Talking about sound, any of you that are in band or play a musical instrument may be familiar with tuning forks, and that's up in the top right. Well, we can go back to the Slinky example that we've used before. Sound consists of longitudinal waves, mechanical waves, and most humans are able to hear from about 20 hertz to 20,000 hertz. Now, that's a variation, and as we age, we tend to lose that higher frequency hearing. You may every now and then notice that if you've got a dog, he kind of tilts his head when he may hear a sound that you can't. Dogs can hear much higher frequencies as well. And some of you may have even downloaded one of those mosquito ringtones for your cell phone, because you, being a teenager, can hear higher frequencies, than your teachers and parents. So as we age, we lose the ability to hear some of those high frequency sounds. And so when you download those little mosquito ringtones, you can hear those sounds, and I, and possibly your parents, cannot. Frequency is, we'll talk about it a little bit more in a couple slides, but frequency, if you think of it, just how often that sound is being reproduced. And as that becomes more rapid, as it increases, we hear a higher pitch. So we can't actually hear frequency or see frequency. We as humans hear the pitch, and we hear increases and decreases in pitch, and that should relate to increases or decreases in frequency. Sound versus noise. Sound is nice, regular repeating, and noise is kind of all jarbled. Maybe sound could be more pleasing to the ears, whereas noise is almost a little painful. When we're comparing the two side by side, or top to bottom, I should say, not side by side, it's good to look at and kind of see the relationships. So the very top diagram, that's a transverse wave, all in blue, and then a compressional wave with the red and blue. So it's not that one is turning into another, just watching them move side by side. And then the drawings right below, where you can see the compressions and refractions maybe a little bit more clearly than on some of the prior drawings. So take a moment and make sure you sketch both of these into your notebook to add with the other notes, because I know when I'm talking it takes some time, so I'll pause and give you a moment to make sure you have all of those details on your paper. When we talk about the speed of sound, a common misconception is that the speed is dependent upon the density of the medium. I've even read that in books sometimes. But realistically, we have to think sound travels through air, but if you have a soundproof room, maybe you've got thinking of the band room or another room where you're trying to make music, you don't want everybody else to hear it next door, so you can have soundproof walls, and those walls are going to be much more dense than air, but yet sound cannot travel through. So realistically, what affects the speed of sound is the elasticity of the medium. And elasticity may sound a little bit odd, but basically think about how much the molecules can vibrate. Atoms and molecules that make up metals are tightly packed, but vibrate very, very easily. So sound travels very quickly through metal. If you look at the table at the bottom of the screen, the speed of sound through steel, for example, is 6,100 meters per second, whereas the average speed of sound in air is about 343 meters per second. It's a huge difference. That's why years and years and years ago, people would put their ears down on train tracks, listen for the train coming through the metal, the train track, because they could hear that long before they could hear the sound of the train coming through the air. Air, because it changes so much, affects the speed of sound in different ways. As the temperature, pressure, and humidity of air changes, so does the speed at which sound travels. On average, the speed of sound in air at 0 degrees Celsius is 331.5 meters per second. And it changes by about 6/10 or 0.59 meters per second for every 1 degree change in temperature. So as the temperature increases, becomes warmer, the speed of sound increases. As the temperature decreases, it becomes cooler, the speed of sound decreases. Though sound travels quickly, it travels very slowly when compared to light. Light travels through space at 3 times 10 to the 8th, or 300 million meters per second, 186,000 miles per second. So when we compare that to roughly 343 meters per second of the speed of sound in air, it seems like sound almost isn't moving. Speed of light decreases based on the refractive index of a medium. We won't get into that right now. We will a little later when we talk about refraction and Snell's law, so don't worry about that so much. But generally speaking, speed decreases through mediums of increasing density. So vacuum, no density, no molecules, outer space, travels very, very fast. A little slower, not much, but a little slower in air, a little slower in water, a little slower through glass. Just kind of a general idea of what's going on. A little bit more with light, or the electromagnetic spectrum. The sun is approximately 150 million kilometers from Earth, yet light from the sun reaches the Earth in about 8 minutes and 19 seconds. And light can travel from the Earth to the moon and back in about 2.5 seconds. Various features that we have of all waves are frequency and period. Frequency, the number of vibrations per unit of time, and that unit of time is typically seconds. Just think of our SI unit of time. So if we're measuring frequency of a wave or frequency of any occurrence, we want to know how often that occurrence occurs in a second. It's measured in hertz, like the rent-a-car, and we can look at it as hertz or in cycles per second, 1/2. Period, on the other time, is the total time required to make one wave, to generate one wave, or have one complete cycle, or for a wave to travel one wavelength. And it is measured in seconds. So you can see there's a relationship between their units. If you will consider the second hand on the wall clock at the bottom of your screen. So imagine the little red second hand is sweeping. How long does it take to sweep or to travel one cycle? Hopefully you said 60 seconds. So therefore, if it travels one cycle in 60 seconds, that would be the period, or the time it takes it to return to its starting position. On the other hand, how many times does it complete that cycle in 1 second? Well, it's not 0, but it approaches that, because it takes 60 seconds to sweep once. So it only completes 1/60th of a cycle in 1 second. So therefore its frequency would be 1/60th hertz, or 1 cycle per 60 seconds. Now think of the relationship there. Period is 60 seconds. Frequency is 1/60 seconds. They're the inverse of each other. Really easy to transfer or move back and forth between. Now when we're calculating wave speed, we're going to think back to that first equation we looked at the beginning of the semester. Average speed is displacement over time, or distance over time, depending on the scenario. Average velocity, displacement over time. But let's just talk about average speed for a moment, distance over time. Well, if we're looking at a wave, the distance of one wavelength that it would travel, or the distance would be one wavelength. So therefore we replace distance with lambda, as we discussed earlier, the symbol for wavelength. And the time needed to travel one wavelength is period. So even though the equation looks very similar, it looks a little different, it's the same idea. So velocity, or wave speed, is calculated by dividing wavelength by period. And since, as we discussed just a minute ago, period and frequency are the inverse of each other, we can also say that wave speed is equal to wavelength times frequency. Waves are kind of governed by a few basic ideas, concepts. So keep in mind that speed is dictated by the medium and frequency is established by the source. So if there's an alarm sounding, that alarm is going to emit that sound at a set frequency. That's not going to change. But as the sound travels through air, through a wall that the sound can transfer through, maybe through water, when the medium changes, the speed's going to change. So the frequency is determined by whatever is creating that sound, or creating the wave. It doesn't have to be a sound wave. And the speed will change, increase or decrease, depending upon the medium.